Hi everyone, I am Annalyn Gumaro. My video lesson is all about vector spaces. So let us take a definition of vector space. Vector spaces is a collection V of a vector and two operation, addition and multiplication by scalars of real numbers. In the plane, a vector described by a pair of x-coordinate and y-coordinate. The tail dot origin and while the head is a coordinate. We can call the vectors on the plane with two-dimensional vector spaces because it takes two numbers to describe each vectors. What do you mean scalars? Scalars are often taken to be real numbers, but they are also vector space with scalars multiplication by complex numbers, rational numbers, or generally any form. So let us proceed the vector spaces or the vector space of R of n. Let U of 1, U of 2, U of n be a sequence of n real numbers. The set of such sequence is called n-space or n-dimensional space and is denoted of R of n. So R of n consists of all columns vectors V with the n components. The components of V are real numbers. So the n-dimensional space is just the space where the points are templates of real numbers. So I have an example of R of 2. R of 2 is a collection of all set of two-order real numbers. So, for example, 0, 0, 1, 2, and negative 2, negative 3 are elements of R of 2. The vector space of R of 2 is represented by usually x and y plane. So, also the R of 3 is a collection of all set of three-order real numbers. We have 0, 0, 0, negative 1, 3, 4 are elements of R of 3. So the set of R of n with the operation of component-wise addition and scalars multiplication is an example of a vector space, and its elements are called vectors. In general, if U and V are vectors in the same vector space, then U plus V is a diagonal of the parallelogram defined by U and V. So another example of R of 3 or 3 vector components. So let U is equal to negative 1, 4, 3, and V is equal to negative 2, negative 3, and 1 be elements of R of 3. So the question is find U plus V and 3 times U. Solution: you add the value of U and the value of V. So the answer of U plus V is equal to negative 3, 1, and 4. And 3 times U multiply the value of U at times 3. So answer is negative 3, 12, and 9. In R of 2, consider the two elements of 4 and 1 and 2 and 3. Find their sum and give a geometrical interpretation of this sum. We get 4 and 1 plus 2 and 3 is equal to 6 and 4. So the vector 6 and 4, the sum is a diagonal of the parallelogram. So let us proceed the properties of vector spaces. We have commutative, zero vector, identity element, inverses, and associative. When we say commutative, V plus W equals W plus V is you can add any two vector under our operation of vector addition. A zero vector, which is adding zero vector, is any vector which is chance a zero vector, the zero having a zero component is called the zero vector. Inverses are also for each vector there's another vector which is point is opposite direction. When you add, you get the zero vector. Associative, V plus W plus Z equals V plus W plus Z. Now that we know that what vector space are, so let's learn about the subspace or subspaces. Let B a vector space and let W be a subset of V. If W is a vector space with respect to the operation V, then W is called a subspace of V. So I have here the theorem of subspace. Let B a vector space and with operation addition, and let W be a subset of V. Then W is a subspace of V if the following condition hold. Sub 0, W is non-empty. The zero vectors belong to the W. Subs 1, closure under addition. If U and V are any vectors in W, then U plus V is in W. Subs 2, closure under multiplication. So if B is any vectors in W and C is in real numbers, then C times V is in W. So I have for an example of subspace, a line L through the origin. So a line L through the origin is also a subspace. Ended L contains 0 and easily said to be closed under additions and scalar multiplication.
Is closed by checking the two properties of closure. First, let's multiply a vector x by a scalar c. Distributing the scalar c, we end up with a vector cx0 negative cx. Notice that this still has the same form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S. Next, let's take two vectors, x and y, both from the set S, and add them together. Provided that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of the first, and once again, we find a result in the same form as we started. This means that the sum is also contained in our set S. We have verified.
So let us proceed the span. The set of all vectors that a linear combination of the vectors in the set v of 1, v of 2, v of n is the set of vector in a vector space of V. Then the span is a subspace of V. The span is the smallest subspace of V that contains that set. The set of S. As an example, let's take a 3-vector thus being of 2, 1, negative 1, 0, 2, 2, negative 1, negative 1, and negative 1. So the span of this of 3 vector will be given by a linear combination of EV1 plus BV2 plus CV3, where A, B, C are also scalars. In a vector for distributing the scalar and then the vector addition to see the span of these 3 vectors to form 2A minus C, A plus 2B minus C, negative A plus 2B minus C, so the span of any numbers of elements of vector space V is also subspace of V. A linear combination. A linear combination, a vector V is a vector space V is called a linear combination of the vector in V can be written in the form E1 V1 plus E2 V2 plus En Vn. Of this vector will be any combination of the using addition and scalar multiplication. So I have here an example of linear combination. We have 1, 2, 3, V2, 3, 5, 1, V3, 0, 0, 8. So the vector of V is equal to 3, 6, 9. So the vector V is equal to 3, 6, 9 is a linear combination of V of 1, V of 2, and V of 3.